Okay, you see my screen okay?
I don't. Oh, there it is.
There it is. Okay, all right, good. All right, so summer packet. I want to just kind of go through the last parts that I find the most important, which is trig, simplifying trig expressions and solving trig equations, and also involving unit circle. So we'll do some of that.
Okay.
I think reviewing arc trig is good. Arc trig here. This is good to review. Looking at a rational function and determining horizontal asymptote, vertical asymptote, and holes.
Okay.
The inequalities, it's good to know, but we'll come back to that if we have time. And then I want to just do a quick review over logs and exponential functions, which hopefully is pretty fresh in your mind since we just got through that. So sigma notation, yeah, it's good to know, but we'll do a little bit of it in calculus, but not a whole lot. And the last page is just trying to figure out what the mistakes are in the equations. So, but it's just kind of hodgepodge of different topics. But I think if we can get through the three big topics here, trig equations, rational functions, and logs, I think we'll be in good shape. So,
okay.
All right, so let's look at number 20 here.
Okay. How would we do A?
Right. So number 20, it says simplify the following. I think an easy way to get that to happen is rule of thumb is every trig function can be written as sine and cosine. So if I can write everything in terms of sine and cosine, I should be able to get a lot of things to match and pair up. So
okay.
give me a moment here. Okay, so simplify the following here. I have sine x. All right, so cosine and cosine we'll leave alone, but tangent, secant, and cosecant, we should be able to rewrite it in terms of sine and cosine. So what we can do with tangent.
What is tangent? Cosine over sine or sine over cosine?
Sine over cosine.
Sine over cosine. Okay. And then secant is 1 over cosine, right?
Right.
And cosecant's 1 over sine.
Right. So I've gotten everything as a fraction, and anything that pairs up between numerator and denominator I can remove.
Okay. So so the cosine and cosine can cancel out.
Right.
And the sine and sine could cancel out. So that means you'd be left with so sine x over cosine x. Which that's the same as tangent x, right?
Yeah, there you go.
Okay.
So that's just an exercise to show that a lot of times if we get everything in terms of sine and cosine, things will pair up a lot easier.
Right.
Okay, so part B, 20 part B. Okay, it's asking us to add two fractions. What do you think we can do there?
Well, our denominators are different, right?
Right, so
we'd have to do something that would make them equal to each other?
not equal, but what we say is we can find a common denominator.
Wait, would it be like 1 plus cosine x times 1 minus cosine x? And then
That's right.
For the numerator, I'd have to either multiply by 1 plus cosine x or 1 minus cosine x?
Exactly, right. So these are significantly different from each other. We can't just say, oh, 1 plus or minus cosine x. So yeah, we need to include both of these expressions to create a common denominator.
Okay.
Yeah. And like you said, we can balance each fraction. So this fraction is going to need to be multiplied by what to match with this denominator?
1 minus cosine x.
Right. So we need to balance that with the numerator. So we need to multiply that through.
And then the other sine x is going to be multiplied by 1 plus cosine x.
Mm-hmm. Right. So we can multiply this through and try to merge as many like terms as we can, but ultimately we can push this together to be one fraction now.
You distributed the signs into the what? Okay.
Into the parentheses, yeah. Okay. What do you see we can do to clean this up even further?
Well, our sine x cosine x plus or minus sine x cosine x, those can cancel out.
Mm-hmm.
And then sine x plus sine x is 2 sine x, right?
Yep.
So that would be 2 sine x over 1 plus cosine x 1 times 1 minus cosine x.
All right. Anything else we could do?
Can we simplify the 1 plus cosine x and 1 minus cosine x?
Yes.
Okay.
All right, 1 second. Okay, yeah. So what if we so what if we FOIL this out and see what happens from there?
Okay. So I get 1 minus cosine x plus cosine x, which is 0. And then minus cosine x squared.
Yeah.
So that's 2 sine x over 1 minus cosine x squared.
Right. All right. There's actually more that we can do. Does this remind you of anything? 1 minus cosine squared x?
No.
There's an identity. Sine squared x plus cosine squared x equals 1.
Oh.
So what can I replace 1 minus cosine squared x with?
sine squared x.
Yeah. Yeah, so sine squared x is the same thing as 1 minus cosine squared x. We make that substitution, and we're left with 2 sine x over sine squared x. So
Would that
this
be
will-
side anymore, or?
yeah, we can go further
Okay.
because what's sine squared x? The same thing as.
And I don't know.
So what sine squared x means is that we're squaring the sine function. There's 2 of them.
Oh, so it's just sine x times sine x.
Yeah. And what does that allow us to do?
Cancel them out, because if you were to cancel one sine x, you'd be left with one sine x up at the top, and then that would cancel out with the other one, right?
Mm-hmm.
You're left with 1? Or no?
Not quite. What's left?
Oh, 2 over.
Yeah, 2 over, yeah. So the 2 is different, separate from the sine x. So the sine goes away, but the 2 is still there.
I see. Okay, so that would mean it's 2 over sine x.
Yeah, which is correct, but we can also move the sine up to the numerator and call it 2 cosecant x. Either is fine.
Okay.
Okay,
Okay.
let's look at part C. So the hint is factoring.
Okay. But how would I factor this?
Right, how do you factor this? Well, what maybe we can do is we can think of what could I create that will multiply to be cosine to the 4th of x? Or how about this? What if I created a simpler version of the problem? Any idea how you would factor this expression?
Yes, so you do x plus y times x plus y.
Yeah. Because I can split x squared up into x and x. I can split y squared up into y and y. And if I pull this out, I get x squared plus 1xy plus 1xy plus y squared. And the 2 middle terms gives me x squared plus 2xy plus y squared. So using that as a model, any idea how you will use a similar pattern to create a factored form?
Oh, you can do this. So that's going to be. Could we do Could we combine the cosine 4x and sine 4x? Or we combine our sine
Not
2?
quite. Yeah. How about let's think in terms of factoring? Eventually, we're going to combine stuff, but you see how we can break x squared down into x and x?
Yes.
And y squared into y and y. So what do you think we can break cosine to the 4th x into?
Cosine squared x?
Mm-hmm. So cosine squared x, cosine squared x. We know that these two our perfect squares of that cosine fourth x. We know that this will multiply to be that. And what can we break sine to the 4x into?
Sine squared x.
So if we were to FOIL this out, would this be the same thing as this?
No, wait.
Okay, let's test it out. Okay, so we're going to FOIL this out just to see if we're actually staring at this at equivalent things. Okay, so cosine squared times cosine squared is
Cosine 4x.
Cosine squared times sine squared x.
Cosine squared x times, or like,
yeah,
sine squared x times.
Let's distribute the sine squared through.
Oh, we do. We do get the same thing, because then that would be sine squared x, cosine squared x, and sine squared x times sine squared x.
Just sine to the fourth of x.
Oh, right.
And then these two terms, 1 cosine squared x, 1 cosine squared sine squared plus 1 sine squared cosine squared equals 2 cosine squared. Yeah, so we know that this is equivalent to, but the reason why we want to get in the factor form is because we're going to see something that will allow us to clean up even further. Any idea what cosine squared x plus sine squared x is?
Oh, I do, because I know it's one of the properties, but I can't remember what it equals.
Yeah, this one that we just
equals 1.
Yeah, equals 1.
So that'll be 1 times 1. So 1.
Yeah. So this becomes 1. This becomes 1. 1 times 1 equals 1. All right. Let's see. Okay, so now we're going to try to solve, but we're still going to factor, clean up, and then, but we may have to kind of recall some of the unit circle values.
Okay.
So 21. Solve the following. And the solution set is between 0 and 2 pi.
Okay, so.
Yeah, so whenever I try to solve a trig equation, typically what I like to do is, if it's possible, if I can get everything in terms of one trig function, then I can compare apples with apples. I won't have to move across different variables, right? So is there a variable, or is there a trig function that we can quickly convert in terms of the other so that we don't have to deal with two separate trig functions?
Oh, we can do the one where it's like the sine squared x plus cosine squared x equals 1.
Yeah, let's use this trig identity here, right? So how would you rewrite this?
That would be sine squared x plus cosine squared x equals 1, but I don't know what to do with the negative cosine x.
So what I would do is, how about this? I think it's easier because there's more cosines than sines. So why don't we leave the cosine alone and convert the sine?
So that would be cosine squared x minus cosine x minus sine squared x equals -1.
Plus 1 equals, right, plus 1. We're just going to replace this piece here.
Oh. But what do we replace it with?
Right. Sine squared x, can we write sine squared x in terms of cosine?
Yes, no?
I can.
Oh.
So is there a way to rearrange these equations so I can replace sine squared x?
Oh, can you do negative cosine squared x plus 1?
Yeah. So I'm going to say sine squared x can be substituted with 1 minus cosine squared x. And that gets us to the goal of, okay, at least everything is in terms of one trig function now, which is easier to work with if I can do that.
Okay.
And this is probably going to be a factoring problem, so let's get everything over to one side.
Okay. So cosine squared x minus cosine x plus 1 plus cosine squared x minus 1 equals 0.
So I'll move these two together. The ones go away.
Right. So I'm left with 2 cosine squared x minus cosine x equals 0.
Factor and solve.
Okay. So
Is there a GCF?
Is it cosine x?
Yeah.
Okay, so that would be cosine x.
Right, so if I factor cosine x, that means I'm dividing everything by cosine x.
Right.
And whatever is left over after the division is going to go inside the parentheses.
So
yeah.
it's going to be, I know it's definitely going to be 2 cosine x, right? Minus 1.
Yeah. And now that we have two separate expressions that are in factored form being multiplied equal to 0, we can basically set both equal to 0 separately and solve for x. So all line down the middle. So we circle here, ask ourselves, when is cosine equal? And just a quick unit circle. All these order pairs. 1, 0, 0, 1. The x value is the cosine.
Yeah, so it's equal to 0 when it's 90 or 270.
Yeah, and we'll leave it in radian form, so it'll be pi over 2 and 3 pi over 2.
Okay, and then when cosine equals 1/2.
Yeah.
Which that's going to be
which will be pi over 3.
Mm-hmm.
And where else is cosine positive?
In the fourth quadrant.
Right. So do you know the fourth quadrant version of pi over 3?
Is that
Same denominator.
5 pi over 3?
That's right. So we have 4 solutions.
Got it. Okay. Oh, so we combined all.
That's
4.
right. Yeah, I found all the solutions and they all landed inside my main. So I want to hold on to all 4 solutions.
Okay.
Okay. Let's go to part E. So there's a relationship between cotangent and cosecant. Typically, it's easier to play with the squared. The squared is easier to replace than the trig function. So if I look at this, I'm saying, okay, if I want to get something in terms of the other, I know I can play with this a little bit easier. So I'm going to find a way to get that cotangent squared in terms of cosecant. Now, you may not know the trig identity, but let me show you a way that you can arrive at it without having to memorize it. So we know this one, right? This is really the only one. Well, not the only one, but this is one that is going to be really helpful. It seems like it's just one trig identity, but there's multiple ones that we can create out of this.
Okay.
So if I divide everything by cosine squared, or if I divide everything by sine squared, a different trig identity will show up.
Right.
Okay. So if I want something that's involving cotangent squared, probably the better bet is if I divide everything by sine squared, because cosine over sine is cotangent. So let's try that one. Divide everything by cosine squared.
Okay.
I'm sorry, by sine squared. All right, let's see what appears out of this here. What's sine squared over sine squared?
1.
Mm-hmm. What's cosine squared over sine squared?
Cotangent x.
X, right? Because I've squared and squared, so it will stay as squared.
Oh, right. Sorry. Yes.
Equals.
And then 1 over sine squared x is cosecant.
Yeah. Secant squared.
Secant squared.
So this is a trig identity that I created out of something we already know. So 1 plus cotangent squared x equals cosecant squared x. You see something that we can substitute.
We can substitute for the 1. We can make it cosecant squared x minus cotangent.
Yes, but I feel like if we do that, we're left with 2 trig functions, which I don't find it to be as ideal.
Okay.
Is there something else that we can replace?
I don't know.
Okay. What about this piece?
We can replace that. That'd be 1 minus cosecant squared x.
Close. What's cotangent squared x equal to?
Oh, -1 plus cosecant squared x.
I'll put the cosecant squared first. I like to put the negative
Okay.
after the positive term. So let's make that substitute there.
Okay. Okay. So now I can factor it, right?
Eventually, something else needs to happen first.
Well, we need to bring the 1 over.
Yeah, we need one side of the equation to show a 0 before we can factor.
Okay. So that's going to be cosecant squared x minus 2 minus cosecant x equals 0.
Mm-hmm. Can I rearrange it in a different way? That's maybe a little bit easier to work with from a factoring perspective.
Negative 2 plus cosecant squared x minus cosecant x minus cosecant squared x.
Or I like to have this, typically when we factor, we like to have the highest power first.
I see.
And then the constant last, right? So it makes it here. So I think some students can look at this and know what to do with factor, but I also tell students, hey, if this looks too difficult to factor, then create a simpler version of this problem, right?
Okay.
This may not be recognizable, but I think if we think as, well, can I factor this equation, right? Because this is just a simpler version of the same problem. Just
right. Okay. So now that we have that, so we're going to do cosecant x
well, why don't we factor this first so we can kind of just have something easier to work.
That would be x. Wait.
That multiplies to be -2 and adds it to be -1.
Right. So it'd be x minus 2 and x plus 1.
Yeah. Good. So now instead of using x's, we'll use cosecant.
So cosecant x minus 2 times cosecant x plus 1.
Good. Okay, we have factor form. We have 0. Draw a line down the center. And then set each parentheses equal to 0.
Okay, so for cosecant equal 2.
So this looks a little bit strange because we typically like to think cosine a tangent. So cosecant of x equals 2. Is this something that's related to cosecant? Maybe we can have an easier time thinking about.
1 over sine.
Yes, 1 over sine. So what if we just solve for sine?
So when sine equals 2.
Well, what if we cross multiply? Maybe easier to see it.
Okay. So 1 equals 2 sine x.
Mm-hmm. So
Okay.
what's sine x equal?
Sine x equals 1. No, sine x equals 1/2.
There we go.
I see.
So we'll come back to this because we can find this on the inner circle.
Mm-hmm.
Do this one.
Can I cross multiply?
Eventually, but
I guess first thing I would need to do would definitely be cosecant x equals -1.
mm-hmm.
And then I could cross multiply.
Okay. What's cosecant x same as?
Oh yeah, 1 over sine x equals -1. Sorry. And then I can cross multiply. And now it's going to be, I got negative sine x equals 1.
Which is the same thing as sine of x equal to
-1?
Yeah.
I'm guessing that's not on the unit circle.
It is. So unit circle. Where's sine equal to -1?
Oh my goodness. Pi.
That's the x value.
Oh, wait. Sorry, y value. Cosine would be pi. So this is going to be 3 pi over 2.
Yeah. Okay, and where's sine equal to 1/2? Well, it's not going to be pi over 3. It's actually going to be down here at pi over 6.
Okay.
Now, where else is sine positive?
In the second quadrant.
That's right. So what's the second quadrant variation of pi over 6? That's the same denominator.
It is 5 pi over 6.
Good. So we have 3 solutions. Okay.
Okay.
Yeah, taking a crash course through pre-calc, hitting all the most important things that we could use or that we will use in calculus. Yes. Okay, so let's go to 25.
Okay.
I'm sorry, 24.
24.
It says state horizontal asymptote, vertical asymptote, and holes for each of the following. This is a rational function here.
Okay.
And what we're going to do is we're going to factor everything that we can. And once we get everything in factored form, it'll be easier to find all these pieces that we're looking for.
Okay.
So, going to factor the numerator first.
Okay.
Multiplies to be a times c, adds it to be b.
Let's see. Okay. 2x.
So what two numbers can you think of multiplies to be -8 and adds it to be -7?
Multiply to be -8 and adds to be -7. 1 and 8.
Okay, what are the signs going to be?
What do you mean? Sorry, I'm just a little. Wait.
So 1 times 8 will be positive 8, right? So it's not going to quite get there. So which one is negative? Are they both negative? Is just one of them negative?
One of them will be negative, and it's the 1.
Okay, let's try it. So -1 times 8 is -8. That's good. What's -1 plus 8?
Oh, that's not -7. That's +7. So it'd have to be -8.
Yeah, let's double check it. So 1 times -8 is -8. That's good. 1 minus 8 is -7. We're in the clear. we know that we found the numbers that will get this to be factored form. Okay, so we'll look at the denominator, the leading coefficient, which is going to be helpful. So we know it's going to be x plus 1/2 and x minus, and this can reduce, so it's x minus 4. So x plus 1/2, x minus 4. Now, if I have this in factored form and there's a leftover fractional denominator, I can pull that denominator in front.
Got it. Okay.
So I have the factored form of my numerator, which I'll put together in a minute, but let's focus on the denominator there. Okay, try this one here.
Okay. So our A and C is 12.
Mm-hmm.
And our B is 7. And okay, so well, sorry.
Yeah, multiply to be 12 and add to be 7.
Right. Okay, hold on. Oh, 4 and 3.
Okay.
And
What do we put in these spaces here?
Could you explain what goes in those spaces, sir? I don't normally use this method, but it seems like it works better than how I normally do it. So.
Okay. So what goes in this space is the leading coefficient. So because it's not as easy as ones that don't have a leading coefficient, so we put a 6 there. So help remind us that you got to deal with that 6.
I see. Okay. So then it would be.
Then we can reduce these fractions if possible.
So that would be x plus 2/3 and x plus 1/2.
Yeah.
And then bring the denominators out front, and that's 3x plus 2. And 2x plus 1.
Yeah. Good. So that's the denominator's factored form. So I'm going to replace the numerator with the factored form and denominator with this factored form.
Okay.
So we're going to work with this form for now. I think this is still going to be helpful for one of the things we're looking for, but it's going to be helpful with the factored form.
Got it.
So we're looking for vertical asymptotes, horizontal asymptotes, and holes. So here's what we can do with vertical asymptote. Comes from the denominator. So we set the denominator equal to 0. And then we solve for x.
Okay, so 3x plus 2 times 2x plus 1 equals 0.
Right. Now, there's something that looks very similar to vertical asymptote, and it's going to be a hole.
Oh.
And hole is a denominator factor that matches a numerator factor. So compare numerator and denominator. Do you see anything similar?
No. Oh, wait, yes, I do. The 2x plus 1.
Yeah. So the whole is going to come from the 2x plus 1. It removes itself. You can cancel it out, but there's going to be residual. There's going to be something left over, and that's where that hole is. It's not quite as big as a vertical asymptote, but it's still going to leave a mark on the graph. So we set that factor equal to 0. We solve for x, and that's going to tell us where that hole is in the graph.
Okay.
Now, vertical asymptote is going to be a denominator that does not match with the numerator. So
Okay.
just that 3x plus 2.
So then that means our x would equal -2/3?
Yeah, that's right. There's my vertical asymptote. And my whole
is x equals -1/2?
Okay. Now the difference is that a vertical asymptote is a line, is a vertical line.
Okay.
But a whole is a what?
It's
a point that's not there.
Point that's not there?
Mm-hmm.
Okay.
So what a whole could look like could be this.
Oh. Okay.
Yeah, so whole is here. So that's what a whole would look like. So that means if I want to find the whole, I have to find the y value at of that whole as well. So the way you find the y value is you insert the x value into the remaining expression that does not include the whole. So what's the reduced expression if I were to remove the whole?
That would be x minus 4 over 3x plus 2.
Good. So if I were to insert the -1/2 into this expression, the y value would be where that whole would be.
Got it.
Now it's going to be a little messier. We may need a calculator here. But I just want to make sure that you can see how we can find that value.
Oh. And then you plug in the whole
Right.
for
Right. Full expression, and whatever number you get, that's the ordered pair. That's the y value of the ordered pair of that whole.
I see. Okay.
So that's going to give us -9. Give us -9. So the whole is going to be -1/2 -9.
Oh, okay. So the whole is equal to an x, and basically whatever value they give you is the y, or
Whatever value that you insert the whole back into the expression without the matching parentheses is the y value of the whole.
okay, that makes sense.
Yeah. Now the third thing that we're looking for is a horizontal asymptote. Now horizontal asymptote, the easiest way to find the horizontal asymptote is to look back at the original expression. Okay. So for horizontal asymptote, we're going to compare degrees, or compare the highest degrees. Whenever we say degrees, we just automatically mean is the highest degree of the numerator and denominator.
Okay.
So the first option, which is one that you're going to see a lot, if degrees are the same, then my horizontal asymptote is the ratio of coefficients. So let's look at this problem here. What's the degree of my numerator?
I don't know. How do you figure that out?
The highest degree of my numerator. Basically, what's the highest exponent that you see?
2x squared.
Yep, x squared. What's the highest exponent in the denominator?
X squared.
Yep. They match?
They do match.
They do match. So the degrees are the same, then the horizontal asymptote is simply the ratio of the coefficients. So now that they match, we just look at the numbers attached to them in front. 2/6, which reduces to be
1/3.
There's my horizontal asymptote, 1/3.
I see.
Okay. Second option. Now this is the answer for our problem. Let me go through the other scenarios here. If degrees is higher in the denominator then the horizontal asymptote is y equals 0. Okay, so here's an example here.
Okay.
Okay, what's the degree in the numerator?
The highest to x to the 5th.
In the numerator.
Oh, in the numerator. Sorry. X to the 2nd.
What's the highest degree in the denominator?
X to the 5th.
Which one has a higher denominator? Or sorry, which one has a higher degree?
A higher degree. That would be the denominator.
Yeah. So as soon as your denominator has a higher degree, we don't look at anything else. We just know that the horizontal slope must be equal to 0.
Okay.
Okay. Third scenario. Any idea what that third scenario could be?
Something to do with if the numerator has the highest degree?
That's right. If the numerator has a higher degree, then we don't have a horizontal asymptote. We may have a slant asymptote, but that's something that we don't have to worry about, not in this course. So for instance, let me look at this here. What do you notice in this equation?
The numerator has the highest degree, so we have no horizontal asymptote.
Yeah, you got a 4 in the numerator, you got a 3 in the denominator. 4 is higher than the 3. There is no horizontal asymptote.
Okay.
Okay, why don't we try one more, see if we can put it all together.
Okay.
Okay, all right, let's look at number 24B.
Okay. So 5x squared. Okay, so for the numerator, our A and C is 5.
Oh, before we do that though, let's find GCF first. We only do the 3 term if after we get through all the common factors out.
I see. Well, so for the numerator, it's 5.
That's part of it. Anything else?
5x.
Yeah, 5x. Yeah.
So 5x times x plus 4.
Mm-hmm.
Okay. And then the bottom. The denominator we can take out x, right?
Yep.
And then we're left with x squared minus 3x minus 28.
Now we can factor this piece, right?
I see. Okay. So that's going to be I think that's going to be x minus 7 and x plus 4.
Mm-hmm.
So -7 and +4.
Let's reset and get everything laid out together. All right, do you see anything common between numerator and denominator?
Our x plus 4s.
Okay. What else?
I don't see anything else.
Hmm. Okay, what if I did something to make it a little bit easier to see it?
Okay. Oh, and our x's.
Yeah, the 5 and the x looks like they're connected, but they're just next to each other.
Okay. So I have 2 holes.
Yeah, 2 holes. Yeah.
Okay. So x plus 4 and x.
Okay.
Vertical asymptote.
Well, for holes, what we're going to do is we're going to set equal to 0, solve for x, and then look for the y value as well.
Oh, okay. So x equals 0 and x equals -4.
Yeah. Now, we found the x values of the hole because the hole is an ordered pair. We also need to find the y value. So here's the reduced function here.
So 5 over -4 minus 7, 5 over -11.
Yep. Okay. And then
5 over -7.
Yeah. So we have two holes.
That's going to be -4 and -5 over 11 and 0. 5 over -7.
Yeah.
Okay.
Good.
Then I find my horizontal asymptote.
You can. You'll have to find that first.
Sure.
Okay. Okay. Compare degrees between numerator and denominator. So I would go back to the original here.
Okay. So the denominator had a greater degree.
Yeah.
So that means y equals 0.
Good.
What's the next thing I have to do?
Vertical asymptote.
Oh yes, vertical asymptote. So that's going to be x minus 7, which x minus 7, when you set it equal to 0, equals x equals 7.
Good. It's a line, so there's nothing else that we need to find. We can just set that that factor in the denominator that has no match in the numerator equal to 0 directly, and be a line. Yeah. Okay, good. We didn't quite get to the logs, but we can just do a quick touch up on that next time we meet, and then we can get into chapter 1.
Awesome. Thank
Okay.
you.
Yeah, and yeah, I'll see you next time.
Yes. Thank
Okay.
you.
Okay, bye.
Bye.
Baby, I did it. Lisa.
I'm so sorry. I didn't realize my door wasn't closed all the way.
Sorry, baby. I couldn't walk over there and tell you.
Sorry, she hurt.
I don't know. I'll listen to the recording to see if it came through.
I'm so sorry.
It's okay, babies.
Did you text me?
And it probably didn't come through. I don't think it was